Before we move to the next topic of our lecture series, let's talk about a little bit more about finite volume method. There is another approach to finite volume method than the one that we considered last lecture, and it is based on so-called vector-invariant form of the momentum equations. So let's start with let's remind first ourselves what vector-invariant form is. So normal form of the momentum equation, or advective form, if I wrote it in vector notation, it looks like the following. So let's ignore Coriolis force and other things, but just in this form. So this is your advective form, where del is just this vector, three-dimensional vector of three-dimensional gradient vector. So it's a vector with components, derivatives along the axis. So dot is a dot product of velocity vector and this vector. So this is just normally you've seen this in your dynamics class. This is just a vector form of equation for rate of change of velocity. So you know also from your dynamics class probably that the same equation can be written in so-called vector-invariant form involving vorticity. So if we define vorticity, so vorticity, you know that vorticity vector equals to vector product of this del vector and velocity vector. So you can then write this same equation in vector vorticity form like that. Equals to minus 1 over rho gradient p. And actually here we have another term because of this. It's a gradient of velocity vector squared divided by 2. So without density, it's just basically like kinetic energy. So gradient of kinetic energy. So now we don't have this kind of all this ddx, ddy kind of here explicitly. We need to know vorticity vector. And vorticity, how let's now switch to two-dimensional form. So let's point our coordinate system, local one, along the velocity vector. Then we can write just in scalar form that the velocity, so in 2D, we have dd du dt, so it's just velocity, it's not component along x direction, it just, well, in this case it is, but so we just use this is our u, so we just consider kind of equation for this direction along this velocity vector. So we have plus omega times, well, don't put just u, which is perpendicular to this vector, right? Because of this vector product. It's a vector product, u is horizontal, like that, and vorticity is in this direction. So vorticity, let's say it's pointing into the board. So this is omega vector, and so your vector product omega in this direction and u in that direction. So you remember this rule how to compute the vector product direction. So you move it like that, so it's rotating like this. So your u perpendicular to the vector is going to be this direction. So it's perpendicular. So it's sometimes called just perp vector. And that's short for perpendicular perp vector. Perpendicular vector to your vector. Okay, so it's like that, and equals to minus 1 over rho gradient p. This gradient p just gradient along this direction of your velocity, minus gradient u square over 2. So of course we need to know this perp vector, right? So in Cartesian grid, this is just normal. U is your component, say, along x direction, and perp vector is actually just a vector along y direction, like v. So this is basically in 2 dimensions on Cartesian grid. This is just there is no really difficulty of writing it. But here we don't consider that. We just consider this kind of local u, which is has local coordinate system. And if you move to another u in another place, coordinate system will change such that now u is again aligned along your local coordinate system, so that you have only one equation. So this is nice. Now we need to be able to compute omega, and we need to compute omega without actually using definition of omega, which is in 2 dimensions. So omega equals to d v d x minus d u dy, and so if we have regular rectangular grid Cartesian coordinates, then it's no problem computing these derivatives. But again, we have this kind of arbitrary grid, and so we basically don't use global x, y coordinate system, only a local one that is this specific place. So instead of computing omega like using derivatives, we will use Green theorem to apply and to actually compute it differently as a control integrals. So let's apply Green's theorem. So we will just write that integral of omega dA of this area A, which is just integral of this dv dx minus du dy, and this area A is just some grid area associated with this velocity, some small area on the grid. So, and according to Green theorem, it's equals to control integral of this vorticity vector, velocity vector, from that dot product with vector L dl, which is which is a vector along the as a kind of tangential vector along the boundary. So let's see. So we have some area A, and then we have u and v in that of some vectors. So this is vector, well, it's a counterclock, remember, like last time. Yes, a counterclock should be, which is this direction. So it's a dl, and vector u can be arbitrary direction in this point. It can be like this. So this is your u. So your dot product is basically it's projection of this vector into this L vector. So this is your u dot dl. This one, this distance. Okay, so when we wrote before, it actually can be written on in Cartesian grid, the expression that we used before in previous lecture, but generally it's like this. So what it means that now if we have, so it means that it's just a component of velocity vector projected into this boundary and integrated along that boundary. And this is what equals to integral of the vorticity in that area. So, or it's equal to some average vorticity of that area times area. Remember how we defined area. So this average we will take as this just vorticity in that grid cell, for example. And then we can actually compute vorticity using just integral along the boundary that surrounds this point where omega is defined. So instead of differentiating, we just integrate along some border. So let's, for example, let's say that we have a grid like the following. Okay, we have some grid cell like this, and let's say that we have vorticity here, omega. So, and then we define velocities here u, and u. And these velocities are along this. They can be different directions, but along this boundary. Then omega, this average omega, equals just this velocity times this length. Let's call it L. So this is 1, 2, 3, 4, and this is I. So this one is Li distance. This is L4, and so on. So then, and this, let's say it's area. Then we can write that this omega equals 1 over area, sum of u I, L I, sum total all I of these sides or edges of this polygon which is surrounding this omega. So you see that in order to compute vorticity, you don't need to compute derivatives. All you need to do is just integrate along this contour around your place where you're interested in vorticity. So, so this is very neat. So this is in the spirit of finite volume. You replace derivatives with some integral statements, and it's relatively easy. It's easy to compute as long as you have this use in there. So this is why. So now let's look more closely into this equation. So what we do now. So now let's consider some so we consider only this equation here. So let's consider some grid, some non-uniform grid, say that's kind of consists of quadrilaterals, triangles, whatever you name it. And we consider a C grid. So you remember a C grid in one of the lectures that we talked about Arakawa grids. C grid is when scalars are defined somewhere in the middle of a polygon, and velocities are defined on edges. In that case, it's very easy to define because velocities on edges, you can compute easily fluxes, and then you can compute divergence of the flux. And in order to say how much stuff is actually added or subtracted of the scalar stuff in the middle of that cell. So so now let's define velocities at the centers of those edges somewhere here. And now we defined scalar point here. So this is going to be our P, where our P is defined for our gradient. And then we assume that on the next, on neighboring cells, so we need to generate this grid very carefully, that it's actually other P's for other cells also along these lines which are perpendicular to our edges. This grid is called orthogonal grid. The grid and this is orthogonal. So, well, it's not quite orthogonal here, but okay, let's put it more orthogonal. Here's another P. These distances to another P may not be the same, may not be, so it's not this distance equal to this distance. It can be arbitrary, it can be different. But what is important that they actually kind of intersect in more or less perpendicular to those edges. It may not be exactly perpendicular, but close enough, so that we could actually use this method for that. So these are P's of other grid. So now we define our U's. You see, U should be, on the right hand side there is gradient of P. So gradient, so U should be in the direction of gradient. And what's the direction of gradient? Easy to compute here. If you have 2 points, it's along this line. So gradient is basically gradient of P equals to this delta P divided by this distance D. So this distance is D. So you see, now we, instead of again computing this complex thing, we just basically directly compute gradient and just distance over this distance. So, so now U is now defined as looking towards the center or away from center. It doesn't matter actually how you define it. It can be some points your positive U can be defined one way and another. So now what's your perp vector? So perp vector should be to the right, because like if this is vorticity vector, this is wind vector, so you rotate from vorticity to wind. So it's like your screw go in this direction, so your perp vector, if it's this one, is going to be to the left from your velocity vector. So these are U's, U, and to the left, so to the left from this vector, this is going to be your perp. So I noted that with this kind of orthogonal sign. So this one is this to the left, so this is your perp. And here, so this one to the left, so this is perp. And here to the left, this is perp. So okay, so let's so we have prognostic equation for U's, which are like scalar quantities now in this framework. For each of them, you can compute this term easily, because you just you take this scalar quantity P, and you subtract, you divide by distance. This is your term here, and you can of course yeah. So and then you need of course some kinetic energy in the same places as P. So basically, what you take some area mean or area weighted U's and kind of project it in the middle. So you take this U, you square it, this U, square it, you use this U, and you multiply by some weights that proportional to some area, which I'm not going to talk about how to exactly do, but basically, if you think about this grid, there are actually two grids here. There is this prime grid, like that, and there is another grid, that connects all these P's. Let's say that there is some other P here, and then there is this primary grid going like here, and primary grid going like that. So this, so you have, you see clearly, you have another grid. This dashed lines. So this is this grid, and there is this grid, solid lines. So this is your primary grid, and this is its so-called dial grid. What actually dual grid? Yeah. So this is your dual grid, and so basically, in order to well, let's not confuse it for now. So now you have you know how to compute this, guys, to advance your use, to predict your use. But now you need this guy. For that you need this omega and your perp vector. So there is no equation for perp vector. I have to stress it. There is no prognostic equation like du perp. No, there is no such thing, because well, there is perp vector is basically defined as just some vector which is perpendicular to u. But you need to compute it somehow. So first let's focus where we compute omega. Omega is just, we need this, so omega is just defined, you see, can be computed using this dual grid. If you define omegas in these primary grid corners, this is your omega. So you see that omega can be computed by this u, these u's, and they along these lines just integrated along this dual grid. And then this is what's going to be your omega. So this omega, and this is a sum along the dual grid. And then you need to, you compute this omega, and then you average it, say, using again area averages, to this location where u is. So let's say this plus this times some weights, which I'm not going to talk about based on areas, but you can do this kind of linear interpolation or something. And then you need to multiply it by your perp vector, and that way you find this guy. And then all your terms are known, and you can integrate it in time using your favorite time integration scheme. So how to compute? So these distances are obviously easy to compute. You just multiply u's by this, I mean perp vectors. Now how to compute perp vector? And that's what's the most difficult part of this whole thing is. So you need to some formula that uses these u's around this u to estimate perp vector. So perp vector is computed as a function of this u using various formulas, and people came up with various ways of, so it's kind of way of some kind of wave interpolation. On a rectangular grid, a Cartesian grid, it's actually very easy to compute perp vector on C grid. So if you, for example, use a grid like that, so this is your u's on a C grid, and this is your v's, and v in this case is actually perp vector. For u, because they v is looking this direction, u is looking that direction. So v in this point, v, or this u perp, can be easily estimated by this surrounding vectors v. So if it's, say, a rectangular grid with equals delta x equal to delta y, then perp vector for u equals to just average of these 4 vectors, because so this vector u is looking this direction, and v is looking this direction, and these vectors are looking this direction. They're all ready. So you just average them, and that would be your perp vector for u. So on this grid, it's very easy to compute using all these vectors. So now on this grid, your u's actually everywhere are u's. They just have different direction. But this perp vector is equal to just 1/4 of those u vectors, like this u, these surrounding u's. It's like 1/4 this average from 1 to 4 of these u vectors, ui, from 1 to 4. So perp vector in here. And so in a Cartesian grid and in a regular grid, it's very easy. And but on this grid, it's a little bit more difficult, because now you see they all kind of looking in different directions. Here they all look kind of this direction or that direction. So to look, and they're perpendicular already to each other, these 2 directions. So it's easy to compute perp vector. But on this grid, it's not easy. So that's the whole new lecture, that how to compute this perp vector on this one, and I'm not going to go into that detail. You can find some various articles if you're interested that actually deal with that issue, but it's relatively simple. Also, it's kind of involved, instead of just 1/4, it's actually sum of some of these vectors with various weights that you can compute. So we assume that this is known, but hard. And so that's basically the essence of this. And many models actually use this method that finite volume models based on finite volume actually use this method rather than the method that we talked about previous time. I actually like that we talked about previous time more, but this method is kind of beautiful and allows you to use finite volume on any grid. There is no x here or y. What we are operating in this method is just basically distances between certain points. There is, regardless of coordinate system, distance is just distance. You can change coordinate system, distance is not going to change. So we're operating only distances and areas to compute certain things. So we interested only in areas, these grid elements, and distances between certain points. So it's completely, it doesn't use any information about local coordinate system or anything like that. And this, and then you get this velocity vector. Wind is actually pointing in this direction, and but the difficulty is, of course, to compute these perp vectors, to compute actual wind in this point. Now the same way you can actually compute divergence. You need divergence to say to compute evolution of scalars, right? Because scalar quantity like ds, dt plus divergence of flux of rho s u equals to, say, 0. So this is S is scalar, like, say, concentration of something, or water vapor content and stuff like that. So it's scalar. So you need a divergence of some flux, and you see flux is u. But here it's actually also this divergence is computed using only contour integrals. And in this case, it's using not Stokes theorem, but Gauss theorem, which actually says in three dimension that integral over volume of divergence of a vector over volume equals to contour integral over area A surrounding this volume of f scalar product with n over area. So where n is a normal vector to that area. So you have some volume and some element here, dA. So this is a vector that's sticking from it. This is normal vector. In our case, so that we have that divergence of vector f, some average sense, in this case two-dimensional, equals to this area times this divergence of f, this average divergence of f, equals to this contour integral around of f perpendicular to f, because that's what normal, times this d, these distances, in this case, that's actually d. Well, that's an unfortunate choice of. So basically what it means, that divergence of scalars are defined here equals to contour integral around this primal cell of perp vectors, because you see they should be, of actual vector u, no, it's actually not, it's perp to this vector, but it's basically just, so divergence of u in this case equals to just sum of this u dl, or du times l I on prime grid. So vorticity was on dual grid, and here is on prime grid. But it's the same. You see, you just take a velocity perpendicular. So this is what your prognostic, and multiply by distance between these omega points between corners, and then add this and add this, and of course looking at the direction. That's important. It should be in the same direction. So there are some sign rule is involved, how you take this control integral depending on a direction. So usually n, normal n, is sticking out. Well, it should be sticking out for Gauss theorem. So depending on that, how you define u, you should add or subtract it when you multiply by this distance. And again, you take this control integral counterclockwise direction. So again, these divergences can be computed again on prime grid using just summation along the boundaries. So no derivative again to compute this divergence are needed. So I'm just talking this kind of conceptual idea of this particular way of finite volume method. And again, the beauty of it, no coordinate system is involved at all. All you have to do is define direction of your main vector of wind that is perpendicular to your edge of your grid element, and also, in order for this method to work, it's actually your prime grid edges should be perpendicular to your dual grid edges, or close as possible. It may not be completely 90 degrees angle, but let's say within like few degrees, and that's actually very challenging sometimes. So you need some specific way of generating grid like this. And all elements may not be just necessarily quadrilaterals that I plotted here. It can be triangles, can be pentagons, anything like anything you want. But again, the prime grid edges should be very close to being rectangle, to be orthogonal to your secondary grid, and that's sometimes it's not possible, or it's difficult to do. But there are methods that actually allow you to do that, and I'm not going to talk about that. And this is basically a very modern approach, state of the art, and many people still working on this method to improve it. And also another difficulty with this method, how to preserve variance of U, because you need that to avoid all sort of issues like instabilities and all. And that's very advanced topic. I'm not going to talk about that, but it's actually possible on grids like that are orthogonal grids. Formulate your algorithm such, especially how you compute this perp vector, that it actually will preserve variance or kinetic energy. I would like to finish this kind of topic of finite volume by the notion of so-called computational modes in space. In one of the previous lectures, we talked about computational mode in time. When you approximate time derivative with time levels more than 2, you create computational mode. Remember, like leapfrog scheme, it's a very good example of that. So it's some bogus solution that actually completely numerically generated, that does not exist in that there is no equivalent in physical solution for that wave. So it's so-called computational mode, and sometimes those modes can be very persistent and can distort your solution pretty substantially. So there are ways to fight those modes. But also the similar phenomenon can actually occur in space when you use not quadrilaterals, but some other like triangles or some other or pentagons or and so on. Why so? The problem is that basically the easiest, the simplest way to think about it, like if you let's say have a rectangular grid like this on C grid. So we're talking about C grid. This is when it actually appears. So you have these points where you defined your U's, your velocities, and in the center you have your scalars or pressure, let's say. So now think about how you generate grid. You basically have this translational symmetry. So you take this element, you move it to the right, and this is another grid. And then you move it north, another grid, you move it here. So this is basically basic element. And this velocity vector is actually shared by this element. So you don't count it as a degree of freedom, because it's the same thing for both grids. So for this particular element, the unique velocities are only on this side. So for each pressure, so one scalar point, you have two velocity points. So here it can be vertical like velocity in this direction, and here in this direction. So you have two equations for them, for each of them. For each of them you have separate equation. One equation for velocity in x, and one equation for velocity in y. And you have p, which is just gradient of that. It's actually acting on those. So you have this kind of correct number of degrees of freedom. So you have two velocity points and one pressure. So the number of velocity points are twice, in two dimensions, twice number of scalars or pressure fields. So in this case, everything is fine. There is no computational mode in space. But let's say that you have a triangle. And to think about triangle, actually, translationally, you cannot make triangle like your neighboring triangle, like look the same. So the only way you can do that, like this is your second triangle, right? So now with two triangles, you can actually move it to this direction and create another two triangles, or move in this direction and create another two triangles. So you see, the minimum configuration of triangles is actually two triangles to reproduce the grid everywhere. So now you have two two pressure points here, and now this is on C grid your unique velocity points, because this one belongs to next element here. So this is your basic, so this I use. So this is your basic thing. So on triangle grid, you need to have at least two triangles to reproduce the grid everywhere. You cannot make this triangle from this triangle just by translation. You need to have, but you can produce the whole grid, like if the grid continues, two triangles can reproduce the whole grid. Okay, so now what we have? We have 2p, two pi's, and 1, 2, 3 u's. But we need to use at least twice as many u's, velocities, than scalars, than pressure. So in that case, we underrepresent velocities, because it should be 4. For 2p, it should be 4 u's, not 3. And that can result in, so now pressure points are overestimated, number of degrees of freedom for pressure, for scalars are overestimated the number of velocities than needed. So for 3 u's you need, smaller than 2 p's, well, not 1.5, but let's say for 6 u's you need 3 p's. But here you have 4, so it's more than needed. And so when you have more p's than needed, then you have some more degrees of freedom in a scalar field. So now you generate all sort of some bogus gradients. So for the same velocity structure, you can have multiple solutions for gradient. For pressure gradient force. And that creates this kind of artificial perturbations or this computational modes, but in this case the computational modes in space, not in time. So now if you talk about, like, say, hexagon like that, so if this hexagon grid, so now you have P here, and you defined your velocities at this hexagon sides or edges, U, 1, 2, 3, 4, 5, 6, 7. Actually, it's not hexagon. Sorry about that. So hexagon should be like 3, right? Something like that. So you have U. So now, what we have here? Translational symmetry. You can reproduce next grid element by just moving this hexagon to the right. So you then don't need this point, this, and this. So this is on this grid you have 1 p and 3 u's. Because you see, unlike this situation, grid made of hexagon, this is another hexagon here, for example. It's obtained by just translation of this hexagon in this direction, that direction. So you see in 3 directions. So you have more degrees of freedom than needed. For 1p you need, for this grid, it's 1p and 2 u's. This is what correct, because you have 2 equations in 2 dimensions. It's 2 equations for 2 velocities. That's all you need to define the system. Your vector has 2 components, not 3 components on a plane. So, but here it's like you define vector on a plane using 3 components, which is overkill, right? So for 1p, you have 3, which is so your number of viewpoints is actually more than needed, and that creates computational mode. So for the same pressure gradient configuration, you can create some other solutions. You have more degrees of freedom of the system than required than a physical solution. And they manifest themselves in all sorts of noise that you can be generated on the grid, or some spurious waves that actually don't behave like normal waves in atmosphere, for example, because you use these hexagons. Of course, so that's the drawback. This is basically why using grids that contain, say, triangles or hexagons instead of quadrilaterals problematic in this point of view. Although there are some advantages of this approach and triangles compared to this approach on some complex geometries, but you need to be aware of this problem, so-called computational modes in space, and they can be controlled. So there are some methods to filter them and stuff like that. But as long as you start filtering your solution, you're effectively losing your resolution, effective resolution. It's fine, like if you make your solution smooth, then you don't really need that high resolution grid anymore. So that's always a bad thing, to filter your solution just to get rid of some disturbances that are, especially like if they are computational mode. Because by filtering these computational modes, you may be filtering your physical solutions as well on these small scales. So that's not, and then you're basically wasting of your resources, computer resources, by effectively running on coarser grid than you actually allocated for. So you allocated very dense, very high resolution grid, but in reality you're running on coarse resolution because you use these filters. So that's a little comment that I wanted to make about these computational modes in space. So they all grid elements with sizes, especially this one is not as well. So this and this, any element grids that consist of elements that are not quadrilaterals on C grid. This is problem specific to C grid. On C grid, because C grid is a way to go for many applications. Because C grid, remember, in order to compute gradients or in order to compute gradients, you don't need to average. Say on C grid to compute, say this is vector here, gradient of your P is in the same direction as U, so you don't need to average. But if you used, say, U defined in like A grid in the center, in the same point as P, then in order to compute dP dx for U, you need to take this U, you need to take this P, average with between them, and then to obtain it here, and then we talked about that when we talked about A, B, and C grid. So C grid in this case is perfect. You no averaging involved to compute gradients. But one additional disadvantage of C grid that in order to compute Coriolis force, you need basically perp, or Coriolis force for U is actually F times V. So you need perp vector, perpendicular vector. On this grid, so you need to average these components into this point, because this point in this vector looks like that, and here it looks like this. So in order to compute perpendicular to this, you need to take this perpendicular vectors average. And as long as you start averaging, you start producing modes that don't see Coriolis force. But on very high resolution grid, when a grid is just few kilometer resolution, Coriolis force is not really that important anyway on this scale. So this is a more problem of when you have a resolution that's comparable to scale when Coriolis force becomes important, which is Rossby scale, right? Rossby radius of a deformation, which is in mid-latitudes, it can be thousands of kilometers or so. So then it's really important. But if you have very high resolution grids, like a few kilometers, this C grid is not going to do any damage to you.